We are delighted to introduce Dr. Amy Williams. She is joining us today as an assistant professor of geology at the University of Florida. So Southern representation in the space sciences. We love it. Thank you for joining us today. She's an astrobiologist and geobiologist, and her research interests include the formation and preservation of physical and molecular biosignatures in terrestrial environments as an analog for putative biosignature formation on Mars. Ooh. She's been a member of the NASA Curiosity rover science team since 2009 and has currently been working with the Sample Analysis at Mars instrument, which is SAM, on the instrument team as a participating scientist to explore the distribution of organic molecules on Mars's surface. She's also a participating science on NASA's Perseverance rover mission, which is collecting samples that can one day be returned to Earth. Exciting updates recently for that. And she received a nomination for the 2021-2022 University of Florida College of Liberal Arts and Sciences Faculty Mentor of the Year Award. And she received the 2022-2023 Provost Excellence Award for Assistant Professors. And she also works towards increasing diversity, equity, inclusion, and accessibility in the geosciences and STEM. So we thank you for that work as well. So let me go ahead and get your slides up, and we are delighted to hear from you.
Should be in this section.
Yes, let's see. Oh.
And then hide actually.
Yes, yeah.
Okay. Sure, it's gonna. Ooh, yeah. All right, we can work a rover on Mars, but we'll see if I can make this work today. It's always the joke. All right. Hi, folks. Oh my gosh. Thank you so much for the invitation to come out and participate in ExplOrigins 2023. Thank you for the hashtag as well. So we've been able to keep up with this on social media. So thank you, Tatiana, for the introduction. Thank you to everyone for the invitation. What I wanted to talk about today is exploration of Mars. And even if you don't explore Mars, I think that you will find this at least entertaining. So I'm going to talk a little bit about what Curiosity and Perseverance both have discovered over the past 10 years, so a decade of discovery on Mars. And so one of the things is that this is not a PowerPoint, this is a Prezi. So we should be kind of bopping around in this nonlinear presentation platform, so long as it is actually working, yes? Okay, great. For folks online. And so I do just want to also say that I am so inspired by this event, by its coordination, by the speakers and the caliber of students that I've met just this morning. And you've really inspired me to want to coordinate something like this at UF, because we have astrobiology across the disciplines and across colleges. And it really is a great place to bring together all of our interests, our collaborations, and our joy with exploring the origins of life and maybe even life beyond Earth. So thank you for that inspiration. And so with that, let me tell you a little bit about the Curiosity to explore and the Perseverance to rove. It's called A Decade of Discoveries on Mars, but it actually is going to need to start a few decades prior to that. So I want to start actually back at 5 decades of Mars exploration. So I at least count myself part of the category of people who have not seen the landing of Viking, but I do distinctly remember Pathfinder and its little rover Sojourner. But let's step back even before that. In the 60s, we sent Mariner as a flyby to Mars. And think about, prior to that, all we could do was look at Mars through telescopes, right? Which is very powerful. But just as we've discovered with our orbital images now, it can be limiting. And so what we were seeing were, this red planet, these dry channel looking features. Maybe they were canals. Maybe there was a civilization on Mars. Maybe that planet was drying up, and so they were trying to channel their water as their last little bit of, natural resource. There were all of these amazing ideas floating around about what might be happening on Mars because we simply couldn't get on the ground to explore. So here's Mariner. We fly by, and unfortunately, we had no idea at the time, we flew by what might have been the most boring part of the surface of Mars we could have. And so we take these images of what looks like this dry, desolate, dead world. And we're like, who cares? There's other things to do. What a shame, right? And so that's why it took a little bit of time to get up into the 70s before we were able to send Viking. And one of the things Viking was meant to do is to look for evidence of life on Mars. So there were 3 experiments that there's 2 Vikings that they took and they performed. Generally, I think the consensus is that they did not find evidence for life, that the experiments did, in fact, give us a lot of information about what kind of salts and minerals were present in the rocks on Mars. But not finding life on Mars did kind of give us a little bit of a setback to redesign what do we want to ask about one of our closest planetary neighbors. So then comes in 96, the Pathfinder lander and its little RC car-sized robot, Sojourner. Now, Sojourner was a technology demonstration meant to show that you can remotely operate a little robot, have it bop up to a rock, perform an analysis, and tell you about it. So that was really powerful because this is the first time that you can operate something that just doesn't land and sit there and do what it can do in front of it that's constrained by how you would land on another world. So from that is the birth of Spirit and Opportunity rovers, the Mars exploration rovers. And they were, of course, incredibly successful for the first time confirming that there was water on Mars. So poor Mariner flying by really just picked the worst possible places to take images, because now what we see is a world where water was flowing on the surface many billions of years ago, but something that we had not necessarily expected. So I don't mean to exclude my lander colleagues here on Phoenix and InSight, but I'm going to, hop over them to talk about the other rover missions that we've landed. So Curiosity, which is still operating today, and then the Mars 2020 Perseverance rover, which you've heard a bit about today already, landed just a few years ago and is still operating. And so in line with all of this, this is meant to be a bit of a trajectory because the next step is something called Mars sample return. I'm going to talk a little bit more. I love all the nodding. Okay, awesome. We are all on the same page here. So Mars sample return is sort of the next step in Mars exploration, and Perseverance is playing a key role in that. So let me go ahead and step back. And what I want to do is tell you a bit about Curiosity, what it's doing, why we're there, and kind of where it's leading us in our exploration of Mars. So I've got a few mission specs for you for Curiosity. And for those of you who are kind of maybe counting, I joined the mission in 2009 as a graduate student. And so I've been able to maintain my position on the mission through a couple of different opportunities. But that was prior to us actually launching. So we launched in 2011, landed in 2012. Our nominal mission was 1 Mars year, so that's 2 Earth years. We now are currently on about 30,735, give or take a sol, which is 5 Mars years or over 10 Earth years at this point. We've driven more than 18 miles in Gale Crater. And so what are we doing on Mars with Curiosity? So, sometimes when I do like media stuff, people are like, oh, you guys are looking for life on Mars. I'm like, no. Really hate to burst your bubble, but no. What we're doing is determining Martian habitability. So what does that mean? That means you want to look for an environment where life would want to live if it were present. And so we're not searching for life, we are searching for the things that life would want and what it would need. So what I want to do is tell you a little bit about Gale Crater and where we've gone to explore. So this is a map of the Martian surface. It is not real color, of course. This is a MOLA map. So the colors are meant to indicate the warm colors indicate the southern highlands. The cool colors indicate the northern lowlands. And so Gale Crater is here along that planetary dichotomy. And so let's zoom in and take a look at Gale. You've seen this image a couple of times today. So this is Gale Crater. It's about 150 kilometer wide impact crater with a 5 kilometer tall mound of sediments in the center. That's called Aeolus Mons, but informally we call it Mount Sharp. And so what I want to do is zoom in on the region where we landed, and you've also seen an image very similar to this today. So we did land in the crater floor, which tends to be a really great place to land a rover. But if you want to go explore anything that has some topography, that means you have to rove over to it. So one of the reasons that we wanted to land in this area is because the Peace Vallis channel, this beautiful carved expression, which means that water was flowing into that crater in the past. And so we kind of colored in, where water might have pooled up against the mountain at some point in the past. So this is one of the first places that we wanted to explore to see if there was evidence for habitable environments where we think water would have pooled. But of course, we also want to explore this mountain, in part because the sedimentary rocks that make up Aeolus Mons record a dramatic shift from a world with abundant water to one that was far drier. And so if you think about how you might read pages of a book, right, to read about the history of something, that's what the sedimentary rocks in Aeolus Mons are like. Each sedimentary layer tells you about the environment at a given time, and you can reconstruct the history of how that mountain formed based on the character of those rocks. So that's Gale Crater. That's where we went. I want to talk a little bit about what Curiosity is doing, what we've discovered, but what we have to start out with is how do you get a vehicle this size to Mars? So Curiosity was way too large to land with the airbag systems that we had used previously. So we had to design a new landing system called the Sky Crane. So this is basically the rover is attached to a rocket-powered jetpack that allows the rover to slow down as you get towards the surface of Mars. When you get to a certain distance, the rover drops on a tether. When all the wheels touch the ground, the tether releases, and the Sky Crane preferably flies off and crash lands somewhere not on top of your rover. And that was a big concern, of course, right? And just so you have a sense of scale, here's some people and here's the actual system set up. Now, think about it this way. You can't test something like this end to end on Earth, right? The atmospheric thickness and density isn't right. There are all these characteristics that you can't just do a full end-to-end demonstration. And so the first time that this whole thing worked from start to finish was the one time that it had to. So we were excited. I would be that person. Yeah. So, right. So you're getting telemetry back and you're like hearing like we did this thing, we did that thing, we deployed, and then you finally get back the image that you've landed, right, successfully, and your Sky Crane hasn't crashed on you. So super exciting. Now we have a new system to deliver a much larger vehicle capable of performing effectively, many of the tasks that we would have an analytical chemistry lab perform without the person. So what are we here doing in Gale Crater with Mars? Well, we are looking for habitable environments. And so what makes an environment habitable? And so what I want to start with is one of my favorite images we took relatively early on in the mission. This is John Klein. This is that lowest area kind of in front of Mount Sharp. And so if there is water and it's flowing downhill as water does towards the lowest point in a basin, this is where it should have been. So we went to John Klein. And even though now this is this desolate, dry, cracked up surface, it does not look very habitable right now, right? But in the past, what we think it looked like was something more like this, a region with ephemeral lakes, water flowing into the basin, a place where life might want to live. And so what is it that we look for when we look for a habitable environment? We want a place with persistent liquid water, the key chemical ingredients for life, and chemical energy for metabolism. And so you heard about photosynthesis today, but there's also chemosynthesis as an option for basically powering a microbial cell. And so what I want to do is actually zoom into our very first drill hole on Mars at John Klein. So our very first peek into the subsurface in John Klein at this particular site called Yellowknife Bay revealed that the red planet is only millimeters thick. This was astounding to me, especially as a graduate student, seeing these data come down and saying the red planet, you look in the sky, you find the red point, it's Mars. I'm not an astronomer. I don't know, my husband knows where Jupiter is in any given, I have no idea. I know how to find Mars because it's red. And it turns out when you drill into the subsurface, in many cases, it's not. So this was just absolutely incredible. So the other great thing, of course, beyond wow, the red planet is not always red, is that we did find all of those characteristics for a habitable environment that we were looking for. Evidence for persistent liquid water. So we were at the end of that ancient river system feeding into a lake. The lake chemistry itself, we could tell, was mild and not too saline based on the minerals and the chemistry of the rock. We did also find the key chemicals required for life as we know it: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And then we did additionally find evidence for minerals in different phases, so different redox phases, where life could potentially perform that reaction to extract electrons from those minerals and generate energy for their metabolisms. So we were able in our first 7 months on Mars with Curiosity to check all of those boxes for habitability. So super exciting, of course, but then what are we going to do with the rest of our mission? So it turns out, of course, a ton. And so what I've tried to do here is, in what we've discovered, summarize 10 years of Curiosity exploration on one slide. So you'll forgive me if I skip your favorite discovery. We can definitely talk about it. So one of the things that you've heard about this morning already, of course, evidence for persistent past liquid water, everyone's favorite conglomerate, at least Tatiana's. So like we landed on a conglomerate. This is a rock made of pieces of other rock, and those rocks only get deposited in that way when you have water moving them into that location. So it does sound like we are trying to evaluate or reevaluate the rate at which water was flowing in these regions. Our initial estimates from the 2013 paper, the way I like to describe it is it was maybe water that was like by ankle to maybe knee deep, depending on when it was flowing. So enough water that like you could probably walk across it, but you'd have to be careful about it, right? That's pretty cool to think about that happening on Mars in the ancient past. We've also found in almost every drill hole that we've made a suitable environment for microbial life. So looking for those key elements and also for minerals in different redox states that could provide chemosynthetic energy. And you can tell some of these are gray. The drill finds show you what the rock would look like inside the drill hole, and some are still red. So there is a diversity. There's not everything is only oxidized at the surface and then reduced in the subsurface. Of particular interest to me, of course, is the preservation of organic carbon in Martian rocks. So having organic carbon doesn't mean that you found evidence for life, of course. Life as we know it is made from organic carbon, but you can also generate organic carbon abiotically through meteoritic processes, or through geologic processes. So the fact that we see it is compelling because prior to the CM instrument looking for this on Mars, we didn't actually have great evidence for organics. Viking was meant to find organics, had a strange reaction that we didn't understand until much later, that is actually a reaction with the perchlorate salts. And so identifying organic carbon, not just that, but actually diversity of molecules is really exciting, not just for the search for life on Mars, but also understanding that the building blocks that you need for life on another world are, of course, present, which you would think they are and you would hope they are, but finally having confirmation, of course, is incredible. Everyone always asks me about methane on Mars. I don't have the answers, but what we have learned is that there's the presence and dynamic activity of methane in Mars's atmosphere. This complicated diagram is just meant to show you that methane doesn't always behave the way our models suggest that it should on Mars, which means that we're missing something. Is it subsurface biology? I don't know. That's one of the things that we consider, that maybe methanogens are generating this and releasing it. Is it geologic activity? Is it something about sort of the boundary in the atmosphere? There's a lot of things that aren't playing the way we expect it to when it comes to methane on Mars, which of course means that we have more to explore, more to question, and more to understand. Every one of these missions also helps us assess radiation risk for humans. So of course, the intent is to send humans to Mars in the 2040s, and we need to know how to protect our astronauts. So one of the things that we do is assess radiation, gamma rays, UV flux to the surface, so that we can develop technologies to do so. And then finally, we do have evidence for a thicker atmosphere and more water in Mars's past. And this is just like a short little like 3-clip video. But these are clouds in the sky on Mars. It's pretty incredible. And I mean, I feel like I could see like clouds moving over the mountaintop here and any, sun setting, beautiful mountainy vista, not somewhere I would have in Florida. And it's just like on Earth. So it's just really compelling and incredible to see. So that is my best attempt to summarize what Curiosity has done in 10 years. And so I want to use that as a springboard to what we're doing with Perseverance. And I'll go into a little bit more depth on Perseverance, just because I've spent more of my time on that mission recently, but I better switch back over to Curiosity at some point here. So Perseverance. So this whole thing is called Mars 2020, because when we designed it more than 10 years prior, we're like 2020. That sounds futuristic and probably like a really great year. Yeah, let's call it that, right? So the name has stuck. And so, we launched in 2020. We landed in 21. We are on Sol 703, I believe, as of today. We have traversed almost 9 miles at this point. So we are making good progress. Some of the things on my mission specs here that weren't on the previous mission, though, are things like a helicopter log. So we have a helicopter, if you weren't aware. Its name is Ingenuity. I can talk about it in just a minute here. But it has completed 42 flights and flown over 8,000 meters. So it's more meters than I personally have flown, like as a person. So it's pretty impressive. Some of the other things on here that weren't on the other slide are samples. So 15 rock cores, 2 regolith samples, and an atmospheric sample. And this is on here because one of the things Perseverance is doing is collecting samples for Mars sample return. And so a new tab I got to add just as of, I think, last week is depoted sample tubes. So these are tubes that are left on the Martian surface in a very specific location to eventually be returned to Earth. And so I can talk more about our caching and what we hope to accomplish with Mars sample return, but these are some of the new things that Perseverance can do. And so our objectives are a little bit different with Perseverance. We're now hoping to understand the possibilities for life on Mars. So we're still characterizing geology. We're still looking for rocks that have high astrobiological potential. And we are collecting those samples so that in future missions, they could be returned to Earth. And so let me tell you a little bit about where we went this time. So we're again on the Martian dichotomy here, but this time we've gone to Jezero crater. So we can zoom in here. Jezero is a 45-kilometer wide impact crater, but it has these really neat features on the western rim. And so let me just kind of zoom into this and get a higher resolution image. Okay. This is a delta or a fan, right? So these things only form when you have water from a river flowing into a body of water. And so when that water flows in, the sediment slows down and it deposits, and you end up with this very distinct structure. So this is Jezero Delta or Jezero Fan. This is one of the things we're really interested in exploring as a habitable environment and a place that we might collect samples that could have evidence for life in those rocks. And even though the delta and the crater itself looks like this today, of course, in the past, we think it looked more like this. A nice crater lake with an inlet channel. The delta would have formed in the water underneath this point here. And there's even an outflow channel from this crater. So there's it's a dynamic environment, or at least it was in the past. And so what we want to understand, of course, is what is its dynamic nature today? So what I want to do is really quickly just talk about some of the things that are different from our previous missions. So what I call the new firsts with Perseverance. So the first is a new entry, descent, and landing system. So although we use Sky Crane again, and as you look at the images of the rovers, yes, Perseverance looks an awful lot like Curiosity, and you build a print from the original bus. But our instrument suite and our capabilities, of course, are rather different. And so what you can do with Perseverance is the onboard computer takes images as it's descending through the atmosphere, compares it to the orbital images in its database, and can actually divert where we're landing to land in a safe place. And that's part of why, as you'll see, we landed where we did out on the crater floor. The other really neat thing that you can do, it turns out, is attach a bunch of GoPros to a $2.5 billion rover and get these gorgeous videos and images. So of course, JPL made this really fabulous video of landing from start to finish, with the parachute deploying, with the rover descending from Sky Crane. And then this is one of, like, this image is really powerful to me, right? That we're documenting ourselves landing on another world, landing this rover. And not only that, but its mission, right? To collect samples that we could return to Earth and hopefully address the question of whether we're alone in the universe. Like, so much promise and potential in that one image. It's just really incredible. So a couple of other things that Perseverance does that Curiosity didn't is that we carried with us a helicopter. So this is Ingenuity. Ingenuity was meant as a technology demonstration to test powered, controlled flights on another world for the first time. It actually has with it a little tiny piece of the Wright brothers airplane. So the very first flight, powered controlled flight on Earth, now sent to Mars. So, we just started out by kind of going up and down from the ground. Then we started flying. The technology demo, just like Sojourner, way before it, was meant to only fly 5 times, demonstrate that we could do this. And as you've seen, we're on flight 42. So part of what we're able to do is demonstrate, in this operations phase, how future rovers and aerial explorers can work together so that we might be able to increase our abilities in future missions. And it actually ends up coming in very handy when we talk about Mars sample return. And then finally, the thing that we're doing this, I keep talking about collecting these samples. So coring rocks on Mars, which we haven't done before. We've collected drill samples, but actually getting a core, breaking it off, putting it into a tube is totally new. So what we're doing, we have the cylindrical drill core, drills in, breaks the rock off at the base, and it's collected directly into a clean sample tube. So here's the rock inside the drill core. And here is one of our, 43 sample tubes. Each collected core is 1/2 inch in diameter and not quite 2.5 inches long. So these are very, very expensive, but very important little tiny rock samples. And so I love this image. This is our cache cam of the rock in the core. And we take these Z-stacked images of it within the core. And then our final image is the hermetic seal that's put on the tube. So it can sit around and wait for us to collect them. And so this is a new image of a couple of our tubes on the ground where we've depoted them. So we're going to have 2 depots for these samples. We have 10 of them at this place called Three Forks in the Jezero crater floor. The other ones, we are still collecting samples, and we're going to depot them at a final depot where hopefully Mars Sample Return can go and collect this really broad range of samples from our entire mission. So those are new things we're able to do. And so I wanted to talk just a little bit about what we've accomplished both in the crater floor and then going up towards Jezero Delta. So in brief, our crater floor campaign was the first, 1.5 years, I think, of our Earth years of our mission. So what we did, so here's the Jezero Delta. And because of that new landing system, when we looked at the maps, the landing system said, this looks like a really good place to land. Nice and flat and not a lot going on here, a safe place for a rover. So although our initial intent was to always go to the Delta, once we're on the crater floor, we wanted to explore what's going on there. And so if you think about it, for the folks who are maybe more geologically oriented, hopefully this is a question that you all can think about. But if you have water from a river flowing into a lake and we have rocks that are part of a delta, what kind of rocks do we expect to see out in the lake basin? Very simple, not trick question. Oh, I heard mudstone from someone who's not a student. Okay, excellent. Okay, yeah. So mudstones, really fine-grained sedimentary rocks, maybe in the lake basin. So we're like, this would be a great place to look for fine-grained rocks that might contain organics. And so what we decided to do was actually explore to the south first before heading north and going around to go to the Delta. So we landed at the Octavia E. Butler landing site, named for the science fiction author. We started traversing south along sort of this boundary between this rougher unit, Maz, and this sort of like linear ridge unit, Zeta. And so some of the things that we see, so at our 2B ridge, we see these kind of flat-lying, layered-looking rocks. Everything's really, really dusty in Jezero. Some of these low paver rocks, we traverse around the point of Zeta here and come around. Some of these like bouldery deposits, you can still see there, it looks like some stratigraphy or layering. And we finally drop down into Zeta here. And here's where we finally see rocks that look like this. So as a geologist, what I see are olivine grains. Olivines are very well known for forming from magmas and in lavas. So it turns out that we actually landed on volcanic rock here in this crater floor. We were looking for mudstones and lake deposits. And so this is actually giving us so much information about not only what happened in Jezero in the past when the sediments were depositing, but that post-depositional erosion and processing over billions of years. So we land on volcanic rock, not necessarily what we expected, but it's probably it's the basement rock that's been underneath the crater this whole time. So that was our crater floor campaign. And just briefly, here are the samples that we collected from those those stops that we made. So you'll see for each one of these, there's 2 cores. So one of those cores goes into that first cache I showed you. The second ones are going to get carried with us and put into our second cache. So that's the crater floor. I wanted to go to the Delta front campaign, in part because I got to be one of the campaign leads for this campaign. So it's near and dear to my heart. I'm going to carry this with me forever, that we were able to explore what we were able to explore with the Delta front. And so again, remember that river deltas are habitable environments. And that's why we wanted to explore this one. One of the great things about Jezero Delta is that it contains a lot of the clays like iron, magnesium, smectites that are really, really good at absorbing organic matter, whether those organics are made by biology, geology, meteoritic infall, everything that's coming from the watershed upstream of the channel and the delta is going to get concentrated down into those delta rocks. And so what we did was we made a beeline from the landing site, Octavia E. Butler landing site, went around Seta because it was actually really challenging to drive through it. Cycle through the animation, hopefully it'll play. And went over to the Delta front, and Three Forks here is where we've depoted our samples. Okay, so if we zoom in and hopefully it stops being digitized, and if it doesn't, there we go. The white lines, just like in the presentations you saw this morning, are always where the rover is going. So we come into Three Forks here, and it looks like we kind of got lost maybe, right? So we went down here to the south because we wanted to explore the contact between the crater floor and the delta. We went partially up, but then we came back down and we wanted to go see the rocks at this delta ascent. So we went and looped around and got those. And then we decided, you know what, we really need some rocks from this delta lobe as well. So we go back across the crater floor, we go up here, collect samples. And I stopped the image here, but we are now, of course, we've gone back, we've depoted. And I think today's planning is the first day that we have officially left the Delta front campaign and gone to the Delta top campaign. So my job today officially wrapped up for leading that campaign. Hallelujah. So what are some of the things that we saw here? So one of my favorite things is this image of what we call Kodiak. So there's this, you can tell that there's this raised feature. It is down gradient from where the delta is. So if you imagine the delta in the past extended all the way down to this feature and probably much further into the basin. So it also demonstrates that there's been extensive erosion of the delta over geologic timescales. And I think this is also just like an absolutely incredible image of these sedimentary rocks with the crater floor lava flows in front of it. So what else have we seen? We finally got a picture of our first sedimentary rocks, these planar laminated sandstones and siltstones. We drove around back up to this place called Hawksbill Gap, and we see these really neat flat-lying sulfate-enriched mudstones. So finally, we've encountered our first sedimentary rocks. Yay, I know, a whole Mars year into the mission. So one of the really cool things I want to point out to you is some really interesting data that we're getting from these kinds of rocks. And so I can zoom way in. So one of the things we can do is abrade into the rock. It's sort of like the rock abrasion tool that was on the MER rovers, but a little bit different. And so as a geologist, it gives us a nice way to see a fresh surface of the rock. When you have a rock that's been eroded and covered in dust for billions of years, it's really hard to see its texture. And so being able to get into the subsurface, even just millimeters like this, is incredibly powerful. And so what we have are a suite of instruments on Perseverance, one of which is an organic carbon detector. It's deep UV Raman. And so what we can do is do these really high resolution scans within these tiny little blocks. And so if you look at the scale bar, that's 10 millimeters. Here's this tiny little block here. If we zoom in on it, what you see is a 10 by 10 scan with our deep UV Raman and fluorescence instrument. And what this is showing you, this is the only hard data I'm going to show you in this whole talk. Each of these stars and the different colors is telling you the wavelength of fluorescence that we see at every one of these points. This is not what we normally see in our Raman scans. So this is what the spectra actually look like, this double peak at these particular wavelengths, 305 and 325. So there's a couple of different hypotheses that we're kicking around for why we see this and why we only see this in these sulfate-enriched mudstones. One of the options is that this kind of fluorescence at these wavelengths can be indicative of organic molecules, things like benzenes and naphthalenes. So this would be consistent with what we've seen with SAM, organics in certain areas, but not others on Mars. One of the really great things is that this sample is going to be, it's slated for Mars sample return. So we should be able to actually address this question of what kinds of organics are present. So I can finally zoom out and just show you all of the samples that we collected, both from the crater floor and from the delta front, including some samples of regolith from a ripple, or a small dune, a big ripple. I know for the Aeolian folks, there's a very specific way to describe that, and I have probably just butchered it and offended everyone, so I'm sorry. So this is the suite of samples, and now we've depoted 10 of these tubes. And so what that really means, and this is sort of getting to my penultimate slide here, these are all for Mars sample return, of course. So Perseverance's legacy is Mars sample return. And once this starts to render, it'll look even prettier. There we go. So Perseverance is collecting these samples. We have 2 depots so that we can select which samples we want to collect. And eventually, and I had on the slide, 26 to 28, looks like 28 is our launch date now. We're going to send 2 additional missions. One's going to land on the surface and one's going to be an orbiter. The landed part of this mission is going to accept samples, presumably from Perseverance, with the aid of actually 2 helicopters. So leveraging our technology demo of Ingenuity to put those samples into a rocket. And for the first time ever, we will launch a rocket off the surface of Mars. It will rendezvous with our orbiter, and we will bring these samples back to Earth to finally have every opportunity to look at these samples with our best instruments, with our brightest scientists, so that we can answer these questions of why are these rocks unique? How are they like terrestrial rocks? How are they so different? Why has Mars undergone such a dramatic planetary evolution that's different from Earth when we started out so similar? And in my hope, it'll help us to address the question of whether we're alone in the universe. Was there ever life on Mars? Is it still there? And how can we continue to explore this really profound question while just keeping in our sense that, we may not be alone in the universe, and how small and precious and rare and unique we may actually be. And so with that, I want to leave you with sort of the broad thought. And my favorite quote is that the universe is a pretty big place. And if it's just us, it seems like an awful waste of space. Thank you so much.
Thank you so much for that wonderful talk, Dr. Williams. I'm happy to pass the microphone around for anyone who has questions.
Hey, awesome talk. And of course, I'm going to ask all about the organics on Perseverance specifically.
Oh, try.
Yeah. So I really loved the slide that you showed with giving us the spatial information on where those organics are.
And I can try to get to them. With Prezi, it's a little bit more difficult. But if you want me to go buzz back there, I can try to do it.
But
okay.
I guess what I was wondering is when it comes to what these different regions on the front of the delta are, why do you think? I mean, you explained why you think the sulfates might be involved in those organics being present, but do you think that maybe on a geological timescale, sort of deposition timescale perspective, do you have any ideas why the organics might be there temporally?
Yeah, it's like the $50,000 question, right? And it's part of what the way that the mission was designed, I think that we will be able to address those questions, but we may not be able to fully address them until samples are returned. Because, one of the things you can do if you want to do sample return is like a smash and grab, right? Go somewhere, grab some samples, come back. You don't need to have a multi-year mission that's characterizing the environment. But if you do it that way, you have the context in the geologic context, the characterization, to answer these questions, I think, way more robustly than a smash and grab. So what we do think that we know about the delta front, like as you've seen, there's extensive erosion that's already occurred. So the delta probably had prograded far greater into the basin than it is now exposed. And what we see at the delta front are, sandstones, siltstones. We actually see some like coarser grain things that might be edging into like sandy conglomerates or gravelly sandstones. And so we're seeing what we think is a turbidite, maybe a turbidite sequence or series of facies. So that seems very logical for where we are in this delta. What's interesting about that particular region with the sulfates. So the image I showed you, we call it hog wallow flats. And like I can talk offline about the really fun naming schemes that we have for things on Mars. We originally informally called it the bacon strip because from orbit, you can see really clearly, it kind of looks like, like a piece of bacon. So we maintain that porcine origin, which I really love. So you can actually see that span across the top delta lobe that we explored, and then actually that lower delta lobe as well. And so it seems like it's at least a regionally continuous feature. It's got all these sulfate salts in it, so it was probably saline and somewhat restricted. So you're seeing these deltaic, maybe like turbidite sequences, but then you're seeing these restricted zones. And then we literally just drove past that and are going into our next units. And so starting to understand where it fits in the stratigraphic context, I think is going to help us understand why you would have concentration there. But it does appear right now to be kind of unique to the delta front. So that was a really meandering attempt to answer a broad suite of questions. I hope I addressed at least one of them.
Yeah, that was great. I was just prying for more information. I got
All right,
a lot.
cool.
So
hopefully you got it there. And we can talk more offline for sure.
So two questions. First one's maybe a bit of a silly question, but so I'm always struck by these images of the sample tubes that seem just plopped on the surface of Mars. It's like they're just sitting there. And is there any concern with Martian dust storms covering these up, making the recovery more difficult, even potentially moving these things?
Really great questions. So I can say that, like, from my experience working on the campaign as we were characterizing the environment where we were going to drop the tubes and then actually going through dropping them, that we really carefully assessed where we were dropping these. And they weren't just like, dropped on the ground. It was extremely carefully selected. Like in one case, there was like a little tiny pebble. And the engineers were like, nope, can't be in this particular like radius from where we're going to drop the tube. So like, nope, we're going to move over a little bit, right? Because you don't want anything that might potentially be an issue for grabbing the sample later. So we don't think that there is a real risk of like a storm being able to cover them up or move things. We're far enough away from the dune fields that you shouldn't have migration that would cover things up. And so we're looking at launching in 28, returning in 33. And so, so it's 10 years from now for these samples that were just depoted. But you wouldn't think that there's an issue with them being covered up with the dust or the sand. And I always point out to people, it's not like in The Martian where like the wind on Mars can blow Matt Damon away. It's really, really low pressure, right? So it actually it's not really moving very much at all, right? It's moving those finer particles, but it's no longer moving big things.
Yeah, that was the one thing they got wrong, right? But so sort of related to that though is, clearly there has been a large amount of erosion in this, like mass transfer. So what was driving that mass transfer then?
Gosh, again, if I had these answers, I would be famous, and that would be fine with me. So one of the things that I've thought a lot about working on both missions, and the same with Gail, and I think Francis may have similar or competing ideas on this, but what really strikes me is that, so for example, for Gale Crater, we can tell that the sediments actually rose up above the crater rim at some point, and that the material around what is now Aeolus Mons has been eroded away. It's 5 kilometers of material. Yeah. And so then the same, or maybe a similar idea with Jezero, you can tell that delta went way further out into the basin and now it has eroded back some substantial amount. We don't know how much. I think one of the things that makes it difficult to compare analogs between Earth and Mars is that if you have billions of years for wind to blow and water is not there to redistribute sediments and plate tectonics isn't there, like you have one dominant process and you have billions of years, how much can you accomplish? And it is a lot of material to move, right? And one of the questions I get is like, where's it going? And I'm like, I don't know, like maybe it's there are some ideas that maybe in the northern lowlands, there's actually like pretty thick, like lust deposits. Maybe all that material gets resuspended in the global dust storms. And when it settles out, like that's where it's going to go. So I think just like with the methane question, we have so many unanswered questions about Mars because every time you drop a rover or a lander, you're looking at a space, the size of the campus here, right? But then you're not gonna, like, how can you extrapolate that to the whole globe? It's a challenge. So every piece is stepwise, but we learn more with every step.
Thank you so much. That was a great answer.
Hello. So you were talking about the introduction of the helicopter Ingenuity, and I'm curious, what would you hope that future, I guess, airborne type devices on Mars can accomplish? Is that something that we can use to map the surface a little better, or other sorts of sample collection, or how is that going to be applied in the future?
I think, so number one, great question. I think it is being applied actually already. So we're using similar sort of aerial exploration to work on Titan with Dragonfly. So that upcoming in like next decades, but upcoming mission, right? So I think that now that we know we can do powered controlled flight on another world, like it is an entirely new pathway for us to pursue to complement our existing exploration. So, on Mars, can you use it to scout ahead and decide if you want to go this way or that way? As we get better at, being able to lift or to have these be able to fly with maybe a little instrument more than just like a little camera on it, can you do mapping at that level? I think it opens a lot of doorways for us to do science, not only on Mars, but on other worlds as well. And so I'm really excited in the coming decades to see what we get out of Dragonfly and Titan, because I think that's going to be a real test of how much can you push this kind of platform to do science. So I think there are a ton of opportunities, and I'm excited to see where the engineers take it, because I am definitively not an engineer.
Thank you. This is just kind of like a mission design question. So how far ahead are you planning your traverses? Like, do you have candidate campaigns that you're going to do, you're selecting from? Mm-hmm. Are you changing this with data that's coming in from the mission?
Yes to both. So yeah, so what we do, so even before we land, once we decide I should say even before we decide on a landing site, people will come up with ideas like, if you landed, like, here's the thing we want to explore. If you landed here, here's how to get there. If we land there, here's how you get there. Here's what you want to see. Once you pick a landing site, then that gets into more detail, because now you have only one spot that you have to think about. And so even before landing Perseverance, there were landing site Tiger teams that basically said, okay, if our entry descent landing system, directs us over here on the crater floor, what science do we want to do? If we actually landed on the delta, what all would we do? So there were all these different potential paths we could take. And then once we landed, we were like, okay, cool, we've got one of these to start with. And then as far as like the detail planning, so my experience as a campaign lead for Delta Front is that months before we start Delta Front, we say, here was the nominal traverse. What science do you want to do? I mean, it's like the greatest possible question anyone could ask. Like, what do you, Amy, want to do at the Delta Front in Jezero? Oh my gosh, okay. So we have all these planning meetings where people across the team come together to say, this is the compelling science question we need to ask at this location along the traverse. I think we should detour off the traverse by 3 drives in order to go see this thing that might change what we think about Mars, And so it is a team-based back and forth to say, what do we want to do and what can we accomplish with our resources? So we're on a tight timeline. We have restrictions. We have like engineering restrictions, like you can't go up a certain slope angle. So all of that comes into play when we come up with our nominal traverse. And then, of course, everything changes when you are on the ground. So say you're trying to drive up something and, I showed you like we went back and forth across the crater floor like 3 or 4 times, right? There's this one dune that we just, ripple, sorry, that we just kept, like we go up and it was auto nav, right? So like then the computer would be like, we're slipping too much. And so we'd stop. And then every time we crossed this ripple, we knew it was going to be a problem. So things that then you adjust on a day-to-day basis. So it is all of the things that you listed, and it's a constant back and forth, which is why I'm partially celebrating with a campaign, kind of ending, the paper writing is really starting, because I don't have to worry about the day-to-day anymore. I can go back to the weekly level. Great question. Thanks.
Such a wonderful talk. Thank you. So I'm really interested in the mafic, volcanic deposits that are sort of near the delta. And so it seems like the interpretation of that is basement material underlying the lacustrine deposits that have been eroded away, or maybe not.
It doesn't always depend on who you're asking. Go
Yeah.
ahead and finish it, and I can. Okay.
Yeah. So my question is, if that is the case, does that give you a constraint on the water table because of the erodibility of olivine? Yes. Okay.
Yeah. So depends on who you ask about deposits. My Amy opinion that does not reflect anything that NASA is doing. Disclaimer. It makes sense to me that the delta and the lake sediments extended farther into the basin than we see today. And the fact that you are in both what looks like a magmatic dome, maybe, right? It's a magma, it's got olivine crystals in it. And then lava flows around it, like that makes me think that looks like the crater floor, like the basement rock, right? And remember, like I was saying before, there's only such a small region that we explore, right? So do the lake sediments reappear somewhere to the north or the south or much further out to the east? Maybe. We're not going to get to explore that and answer that particular question. So I think they're probably there, and I think they've been eroded away because that finest stuff is going to get eroded away first. But to your question about water table and aqueous alteration, in our suite of crater floor papers, we've identified a lot of aqueous alteration in the basement rocks in the mafic floor. So there's clearly been some water moving through. We see perchlorates, which indicates that's like probably maybe the last gasps of water, but that's also potentially just what's preserved at that stage, right? We're seeing sort of the last little bit of things as opposed to what was happening along the whole evolution of the water table and the aqueous alteration in Jezero over its history. So, yes.
Thank you.
All right, thanks, folks. That was our question period. So we're going to have a little break right now, and then we will be back in 10 minutes, just so that you guys have a little break before the next session where we have 2 more presentations. So thank you again, Dr. Williams.
Thank you.
Oh, okay. Yeah, I think it's like one click here and then, yeah. I think it was fine.
Okay. No one online said they couldn't see it.
Perfect. Okay. Yes. Thank you so much.
Yeah, of course. Now I can just close it.
Yeah.
And then drag it back.
So yeah, I think escape and
There we go.
yeah. Perfect. Oh, I think you need to hit escape. Yes, perfect. Yep. Wonderful.
And then I'll just log out real quick.
Okay, perfect. Yeah, so we can stop. Or no, I guess it's not.
No, I think it's but it's just.
Yeah, okay. No, so this is fine.
I'll leave on this side.
Yeah. Perfect. Yes. Thank you so much.
Yeah, grab my water.
Yes.
Get your talk up there. Awesome.
Yeah. So if you've got the USB, it can go right in there. You're Alisha, right?
Yes.
Okay. So your presentation will be up here. And Heather, let me pull yours up. you want me to pull it to the? Yeah, if you pull it into. PowerPoint. Yeah. Thank you. Let me just see that it ended up in. Yep. Perfect.
I'm used to it being down here.
Right, exactly. Okay. Perfect. Okay. Thank you. And we'll have that ready for you. Oops. Yeah. Let's see. Mhm.
Oh, yeah.
And then. Oh, thank you. Yeah, if you want to steer the mouse for okay, perfect. Yeah. Yeah, okay, so we'll have that set for you. And you're going first. Yeah, okay. Yep. So this is our clicker here. So there's the back and forth, and then this button above them is the laser if you want to use that as well. And then I can be in the front to give you like a 2-minute warning at the 10-minute mark for 12 minutes if you'd like that, or you can also just refer to the time when you have up there. So sounds good. Awesome. Yeah, thanks for. I look forward to it all. My mother's. Yeah, she has. Oh, yeah, yeah, yeah. Yes. Yes. Oh, wait. Yeah, I love that. Pretty similar to most institutions. Sorry. No.
No, I came out of UVA.
Yeah, I don't know. Yeah. Yeah. Okay. Yeah, here. This folks. This is already on. So when it's time. Like, if you have one questions or. Yeah, yeah, okay. Yep, so. Here's the kind of run project. Okay, perfect. All right, yeah, so you will give them. And I'm sure some will. So I was not paying attention. Yeah. Yeah, let's go home. Yeah. Let's go home first.
Does it prevent on here? Oh, okay. Or should we put it on? All right, everyone, we're going to get started with our third session of the day. And so next up is Alisha Vira. Is it? Oh, actually. Yeah, is the sound working? Okay, great. Great. We're going to start for our third session of the day. And our first speaker is Alisha Vira.
Hi, I'm Alisha Vira, and I'm a third-year PhD student working with Dr. Philip First and Dr. Zhigang Zhang in the physics department at Georgia Tech. So today I'll be talking about something different than what you've heard previously, and it's more about designing a boron nitride polyethylene composite for shielding lunar neutrons. So in space, radiation is a problem. Astronauts are exposed to a lot of radiation. They're exposed to galactic cosmic rays, which compose of mainly proton and alpha particles. And they're exposed to solar energetic particles, which originate from solar flares and solar wind. And this consists of energetic protons and other heavy charged particles. So all of these radiation sources can create damaging health effects. Radiation results in changes to the bone and muscle, cartilage microstructures, increased risk of cancer, cognitive decline, and degeneration of the circulatory system. So from the guiding principle of radiation safety, ALORA, the way we minimize this is minimize time, we minimize distance, and we use shielding. So since astronauts are going to be in space, we really want to optimize the using shielding part of things. So what type of radiation is harmful to humans? So we have alpha particles, and alpha particles can be very harmful, but they're easily stopped by, for example, a piece of paper. We can have beta particles, which go through a piece of paper and are easily stopped by aluminum foil. We have X-rays and gammas, which are quite harmful to humans, and they're harder to stop because you need a dense and thick material like lead, for example. And then we have these neutrons that pass through a piece of paper, aluminum foil, a giant piece of lead, and it needs water. And so the water is used to thermalize neutrons, and then we could eventually capture the neutrons using a different material. And this is kind of like one of the few ways we can shield neutrons. And neutrons cause a significant health effect. So for the purpose of this talk, we're going to focus on neutrons. So what do we currently use for shielding? Currently, we use aluminum because it's cheap and easy to work with. We want to move away from using aluminum and instead use high-density polyethylene, which is a high hydrogen-containing component and therefore has a large elastic scattering cross-sections with neutrons. And all this means is that's good at thermalizing neutrons. We could also use hexagonal boron nitride, which just simply contains boron 10. And boron 10 has a large capture cross-section with thermal neutrons. So boron 10 interacts with a thermal neutron and it produces a lithium and alpha particle. And these are heavy charged particles, so they're easily stopped. So they have stopped within a few microns of material. We note that these alpha and lithium particles are produced in the excited state, so they give off a prompt gamma. And these gammas could then go on and contribute to the health effects. So we want to optimize our shielding material using high-density polyethylene and hexagonal boron nitride, try to figure out by adjusting the internal structure of these shielding materials, what is the best way to shield these neutrons. So how do we address this problem? We're going to use Monte Carlo simulations to simulate a variety of different composites and computationally determine the best configuration. For this, we use a CERN-developed C++ code called JANT4, and JANT4 has been used in a variety of different applications. It's been used for high-energy physics, space and radiation, and medical physics. So once we simulate a variety of different composites and optimize our internal configuration, we can then fabricate and experimentally test the effectiveness of these shielding materials, and this is still ongoing. So here's our structure of our GAMP4 simulations. We have neutrons that are uniform, logarithmic space uniform in energy, and isotropically incident on our composite, our HBN HDP composite. So here is the lateral distance as a function of depth, and white shows the HDP and gray shows the HBN. So we have neutrons coming in, shown in green, and they undergo this capture event, and they produce our heavy charged particles, which are shown in red, and they're very small because they have a very short stopping range, and the gammas, which are shown in orange. And what we do in GEONT is we set what's called a sensitive detector on the entry and exit surface. And all this does is that it saves the necessary information at the entry and exit. We could set the sensitive detector to be the entire range, but that generates a lot of data. And what energy distribution do we send in? So when galactic cosmic rays interact with the lunar regolith, they produce these secondary neutrons. And these secondary neutrons have a wide distribution of energies. And what we're mainly consider for this talk is this thermal range in energy. So how do we optimize our shielding for this thermal range of neutrons from galactic cosmic rays interacting with lunar regolith? So there's a variety of ways we can distribute the boron 10 within the HDP composite. We could have a blended structure, which consists of a homogeneous blend of HDP and HBN. And here what we vary is the weight percentage of HBN. So 0 weight percentage corresponds to 100% HDP, and 100 weight percentage corresponds to a pure HBN block, which is actually not feasible to make, but we're just exploring it in this parameter space. We could also have discrete layers of HDP and pure HBN. And here, this is what we call the ideal layered structure. And for this, we vary the loading of HBN, which controls the relative thickness of HDP and HBN, and we vary the number of HDP layers. So here's an example of the lateral direction as a function of depth, and we have this discrete layering of these two materials. So we can't actually fabricate HBN that's a few millimeters thick. So in order to, we need to mix it with some sort of binder. So we explored this, what we call manufacturable configuration, which consists of layering pure HDP with a blend of HBN and HDP. So instead of our pure HBN layers, we then add in a binder, HDPE, and this explores a parameter space that we can actually manufacture. And we compare this to the performance of the ideal layered and blended. So here we're addressing the question of what is the best way to distribute our boron 10 within our HDPE composite. Is it better to blend it, or is it better to have discrete layers of it? So from all of these simulations, we produce like 8,000 different runs. We need a way to evaluate all of these simulations. So to do that, we use what's called the effective dose. And this is a common practice in medical physics, where the effective dose is equal to the sum over the tissue weighting factor times radiation weighting factor times the absorbed dose. And all this means is that it tells us how damaging a particular particle for a given energy is for the human. So here we have a plot of the effective dose per fluence as a function of energy. So the larger the effective dose, the more damaging it is. So as I mentioned, heavy charged particles, which consists of alpha particles, can be quite damaging, but they're easily stopped. Neutrons, shown in blue, are quite damaging almost across all energy ranges shown over here. Gammas are damaging, but only for this high energy range. So by using the effective dose as a figure of merit, we want to explore all these different composites to see what's the most optimal structure. So from doing that, we have these following results. So here we show the effective dose as a function of mass per unit area. So we've shown as function of mass per unit area, as this is a better merit for people who are actually designing these materials. So we've shown a few different reference lines. So aluminum, which is currently used, pure HDPE, which as we increase the mass per unit area, the effective dose decreases, which is what we would expect, and pure HBN, which is not feasible to make, but we've just shown as a reference. So where does our blended, ideal layered, and manufacturable results fall on this map? we end up seeing that the blended agrees with the pure pure HBN at the low mass per unit area, improves upon that, and then agrees with them at the high mass per unit area. So this is a slight improvement upon pure HDP and pure HBN. What about the layered and the manufacturable configurations? So here we see that the layered and manufacturable are both better than the HDP and HBN and significantly better than aluminum. We also see that we have similar performance between the ideal layered and manufacturable, which is good because we can actually make the manufacturable. So here we have two different kind of circles. The filled circles correspond to what we call a tri-layer structure. And this corresponds to 2 layers of HDP and 1 layer of boron 10. And then the open circles correspond to a multi-layer structure, which corresponds to more than 2 layers of HDP. So overall, we've shown that we can improve the shielding effectiveness by 4 times to 30 times over aluminum and 1.5 times 2 times over HDP. And we also know this interesting transition where we change from an optimal tri-layer to an optimal multi-layer configuration. So next we want to explore what happens, how does this optimal configuration change when we incorporate the complete distribution of lunar neutrons? So we're also undergoing fabrication, and the fabrication method that we're exploring, done by Emily Ryan in Dr. Schaffner's lab, is compatible with additive manufacturing. We have actually fabricated some of what we call the manufacturable configuration and done preliminary SEM measurements and Raman measurements. And we've actually sent some of these samples to the Space Force for them to put into low Earth orbit. And we'll get the samples back and see how they've changed to our initial measurements. So once we fabricate the materials, we can also expose them and do ground-based studies where we expose them using the DD generator that produces high energy neutrons at Georgia Tech. And then we can put our samples on the back end of this. So we'd put our samples in the back end to measure the shielding effectiveness and to measure the effects of the neutron radiation on these materials. So overall, we've shown that by simulating these variety of different composites, we can significantly reduce the effective dose and therefore lengthen mission durations and reduce the health impacts that astronauts would have just by changing the internal structure. And next, we want to extend our model to include the full range of lunar neutrons on the surface of the moon. Okay, thank you.
Awesome, thank you. We can take any questions.
Hey, great talk. So I'm curious if you've done any testing to evaluate any kind of like polymer decomposition or degradation as a result of this radiation.
Yeah, so we're not doing those studies. We're kind of attacking this problem from a more simulations point of view. But other labs have been doing studies, at least in the literature, to look at the degradation of HDP and some of these shielding composites upon radiation. That's not something that we're looking at over here.
Gotcha.
So the idea of these materials, right, is that at some point they'll go into spacesuits potentially to protect, or maybe, let's say. So I'm curious about what's the consistency? What are the thicknesses? What would it be like if you had to wear a spacesuit that consisted of this material?
So from this plot over here, we've explored shielding composites that have a range from 1 millimeter to 100 millimeters. And the materials that we're exploring can be flexible, so they can be put into some of these spacesuits. We're also looking at applications where they can be incorporated into habitats or even put on vehicles for shielding.
Any other questions?
Great, thank you, Alisha. And next up is Chad Pozarycki.
Hey everyone. So I'm Chad, and Today, we're going to talk about biosignature preservation and evapoconcentration in 2 different places. I'm going to talk about results from an area in California called South Bay Saltworks, and I'm going to be talking about some of the field work that I did in August in Western Australia. And so hopefully we might come out of it with an idea that following the salt might be kind of cool. And yeah, and I did this work with the Oceans Across Space and Time team, or OST. And so let's start off the beginning. Where are we looking for life? So if we're looking for life on ocean worlds like Europa, we see that we have these stripes. These are very likely salts. And if we're looking at Enceladus, both of these which have subsurface oceans, we see that there is a lot of potential for different extensional features, as they're called here, chaos lineae, and different ways that salt might be swelling, building up, and concentrating on the surface. And so that's sort of what we're looking for on those sites. And then also on the south pole of Mars, potentially controversially, there may or may not be liquid or brine in ice or liquid form. That would be at low water activity or low water availability, which I will talk about a little bit more as we go on. And so in general, what we're looking at are analog sites that give us hypersaline characteristics and low water activity. So a lot of ions dissolved in these waters, in these salty brines. And so these sites, for example, this is Lake Campion in southwestern Australia that we were in August. They can be training grounds for robotic exploration, like rover exploration on other planets. So we can do instrument testing either in the field or bring our samples back to Georgia Tech and working on them here. And so we could look at salt, acid affecting the analyses. And then it gives us a look into the environmental and biological processes. So we're also just learning about these sites as interesting places on Earth. And so this is South Bay Saltworks. And the way that South Bay Saltworks works is you have seawater coming in and moving through these different controlled salt farming basins, where the people working there move things around and allow salt to evapoconcentrate up into those a lot more densely concentrated regions there where it's harvested. And so given sites like that and the sites in Western Australia, we can ask things like, can these biosignatures be detected in high salinity areas with the tools that we have? And what do they mean for our search for life? And so methods. So this is one of the Western Australian lakes. I'm out here kneeling with my very sterile garb. I have my sleeves and my gloves and my mask on. I'm taking field notes all the while, which makes this very difficult. And of course, I have my Australian bonnet. And here's Maggie and Emily from the OST team, and they're working on pumping some water out of the brine there. And it allows us to get very close to the hard salt surface that you can see underneath, getting samples very close to that without stepping on it or contaminating any of the stuff that we're interested in. And that's actually a dingo. It's domesticated. So what analyses do we do? So this is a gypsum crust. Say I bring this home day of in the field, I bring it back to the motel, and we do an extraction procedure on it using these instruments or appliances. So we boil some water, vortex them, centrifuge them, weigh them out before we do all that. And we prep and analyze them for ATP concentration. And we use a luciferase assay, and we get luminescence using this little tiny luminometer that airport security was very interested in. And that gives us a lot of information about the cellular activity of the samples. And as I'll talk about a little bit later, ATP decays very, very quickly in most natural samples. And so that's why we think it's a good indicator of active cells. Other analyses we do, when we take this stuff back to Georgia Tech, we can do capillary electrophoresis, which is just a separation technique, and then laser-induced fluorescence, which we use to, in this case, tag primary amines or look for amino acids. And when we pass it in front of the detector, we can separate them and distinguish which amino acids we're looking at. And of course, we get a lot of information from our collaborators. Here's Dr. Stefan Busecker from Stanford working on gas flux measurements with his GasMet instrument. This is Luke Fisher at Scripps San Diego. He's a grad student who's working on culturing anaerobic microbes. And this is Dr. Sanjoy Som from NASA Ames, and he's giving us geologic context with his rock hammer. And so let's talk about results. And we're going to talk about results from South Bay Saltworks because I have not gotten all the results from Australia yet. So we're going to go back in time and talk about South Bay Saltworks. And so this is the capillary electrophorescence, laser-induced fluorescence data from our South Bay Saltworks samples. And as we increase in magnesium concentration, so decrease in available water molecules, decrease in water activity, we get a huge increase in the amount of amines that we're detecting. Not only do we get this the identified amino acids, but we get this sort of washboard pattern here, which is really interesting because we think there could be other compounds hiding in there. We don't exactly know what they are yet because our standard has not identified them. And we also get these out here. So, compared to our blank down here and then increasing from seawater-like up to hypersaline, this is very, very interesting for detectability. And so we think this is primarily due to evapoconcentration. So this is a paper from Kathy Benison's group, and this explains in the Western Australia lakes how if you evaporate water that has organics in it, obviously it increases the concentration. And so that's a really important effect. And we think that that is a huge effect and maybe the most major effect, but we don't think it's the only one. So if we look here at the breakdown of the relative amino acid concentrations in these samples from from South Bay Saltworks, we have the very hypersaline samples down here, and then increasing in water activity to the seawater-like samples over here, we see different distributions of amino acids. So over here, the glycine is a lot more, I guess I could say expressed, or maybe upregulated, but I'd rather just say is present at a lot higher concentrations in these lower water activity samples, as is proline and phenylalanine here. And so the reason that we might be interested in that is because the prevalence of certain amino acids could belie the osmotic accumulation of certain compounds, which cells use in these high stress areas to protect themselves from exploding, basically, but to keep themselves from damaging their internal homeostasis, they accumulate certain compounds, some of which are those amino acids, and some other ones that we're interested in. And this even happens in halophiles. So even the people that are really, or the cells that are really good at dealing with salt still have to use this process. And so this last figure here shows us the ATP as well. So in gray boxes here, you have ATP. In blue, this is amino acid concentration total. And then in red, we have cell counts via microscopy, which was done by Ben Klempe, another OST member in a different paper. And so down on the bottom, we have magnesium increasing. So low water activity, very hypersaline, hard to live in, and then more seawater-like down there. If we move towards the right-hand side here, our known activity is decreasing. It is very hard for these cells to live in this environment, and it's shown by the cell counts by microscopy. But despite that, we still have this really big increase in ATP concentration, and it even stays pretty high here when we would expect it to be sort of bottoming out. And so we might explain this with evapoconcentration, but here, why is the ATP sustaining? And we'd love to have information there, but our assay actually it wasn't really working very well with the high magnesium concentration. But we may think that this might be due to preservative effects to allow the ATP to exist for that long. And so this is actually mentioned in a paper from 1987, which describes preservation of ATP in hypersaline basins. And they ascribe it to hydrolysis of ATP decreasing because you have less water available, lower water activity. And I think that makes a lot of sense. And so I think that we might have found some evidence for that at South Bay Saltworks. And so in the future, where do we want to go with this? Well, I went to Western Australia, collected all those samples, so maybe we should compare it to those. So first I want to determine, does that increase in biosignature molecule detectability with the drop in water activity that we saw at South Bay Saltworks, does it hold true in Western Australia? I hope it does. I think it'd be really interesting, but that'd be something to test, or maybe it doesn't, and it gives us even more stories to explore. Then we want to continue to investigate the effects that cause the increase. So specifically of those three reasons, which ones most importantly, and how and why, and how do they change for Australian lakes, which are a little bit different, a lot different in many ways. And then also look at solids. So we collected some solid samples, some dirts, clays, some salt crystals, and we want to look at preservation in those. And so, last but not least, conclusions. We have basically shown that these systems, South Bay Saltworks specifically, concentrate biosignature molecules. And if you have instrumentation that allows for detection of these compounds in these hypersaline regions, which is not a given, then it does make them easier to detect. So that could be super, super interesting for looking for biosignature molecules on other planets. Another point is that ATP preservation due to low water activity was observed at South Bay Saltworks and supports the previous paper, and we might see that again in the future. The third point here is to look into osmolyte accumulation more. It may contribute to biosignature detectability, but it also may influence the ratios of amino acids that we would expect to see in certain places on Earth or on other planets. So I just want to acknowledge my advisor, Dr. Amanda Stockton, my senior graduate student who just graduated and is now off to an NPP at Caltech and JPL, Dr. Marshall Seaton, and all the undergraduates who I have the pleasure to work with, and of course, the Oceans Across Space and Time team. So I'll take questions.
Thank you. And we can move into some questions.
Thanks, Chad. Great talk. Very interesting stuff. I was wondering if you could bring it back a little bit in terms of, so you see these accumulations of organic species, but we don't really know how briny some of these oceans are, right? So how does this sort of contextualize with those? What is the likelihood that we would expect to see sort of these salt deposits on somewhere like Europa or Enceladus?
That's a great question. And so I'll take it all the way back to the photos just because I think that's the best place for me to look at. But well, actually, let me show you right here. So these salt crusts here are sort of like when this water is gone, it's salt flats. So these transient lakes, they evaporate and you get salt flats with really thick crusts of salt. I don't know of on Mars there being as robust, thick salt crusts as we see there. And if there is, I'd be super interested in knowing about that. But what I think we do see on Mars is still this evapoconcentration going on and providing evidence for past hypersaline lakes that behaved sort of like this. And in Europa and Enceladus, let me just find that one figure that sort of points at. So these dapiers here and the movement of maybe saline, maybe not so saline water underneath Enceladus onto the surface could potentially concentrate it to be a lot more saline. So Enceladus, from my understanding, is not that saline, but I think some work could potentially have pointed to the surface material being a lot more concentrated. And on Europa, we especially see that.
So great. Thank you so much.
Thanks, Chad. This is really interesting. I'm curious. So for the brines, do you intend to look at other molecular classes besides your amino acids, or have you? Is that part of the plan?
Yeah.
That's the first question.
Okay.
Yeah.
So we right now have developed a method for our CELIF, which try not to make everyone blurry by going all the way to the end, but this is in my bonus slides. So this is our CELIF method that we developed for amino acid work. And it took us a while to develop this. CELIF is sort of difficult at times. And we do have plans to develop for this same instrument methods that work with carboxylic acids and also a chiral amino acid method. But those are all sort of when we get to them things. So that's why I've been interested in potentially moving towards mass spec to look at areas where there's gaps. But yeah.
All right, excellent. Yeah, I'd be really interested in, like you said, with what's in the solids versus what's in the brines too, because that fractionation, I think, is something the whole community needs to try to get more resolution on. So
yeah,
cool. Thanks.
Yeah, thanks.
And it looks like we have a question online.
Yeah, our online question from Clara is, are there any similarities between the soil on those samples from Western Australia and with lunar regolith?
I don't know too much about lunar regolith. I would imagine that there is not too many. I think this is really soil. I mean, it has been processed a lot, has presumably a lot of organic content in it, and it's a lot more clay-like. Lunar regolith, I don't understand it very much, but from what I do understand, I don't think it's got any kind of mineralogy. So if we were to look at lunar regolith through the same lens, I think it would be completely different properties governing any preservation of organics if it was meteoritically delivered.
Great, thank you. And with that, let's give him a hand. And we're going to take another break, and we'll be back at 2:20 with our second keynote from Dr. Abbott-Lyon.
You have to click in the screen.
Oh, got it. Thank you. Sorry. Oh yeah, everything's.
So there's your back and forth buttons, and then this button is the laser. And it's presenting like so it does your instruction. Yeah. Let's try to keep. Yes. But I don't go too long. I see what the camera is too. No, it's my setup's just automatically. Didn't have to figure it out. Right. Well, it's also good to know if I walk across the other side, I'm actually walking across the camera. They can see me as long as I stay on the screen. Right. But feel free to wander right now. Yeah. When I'm teaching, I actually yes. That definitely gives me away. Yes. It's a good trick. All right, folks. We'll be getting started in just a minute here. All right. Thanks, everyone. So I'm delighted to be introducing our next plenary speaker. This is our last speaker of the day after we've done our oral sessions and heard from our 2 keynote talks. So I'm delighted to introduce Dr. Heather Abbott-Lyon. Dr. Abbott-Lyon is an associate professor of chemistry at Kennesaw State University, just north of Atlanta in Kennesaw. So we're delighted to have her today representing astrobiology in Atlanta. She received her PhD in chemistry from the University of Virginia and is in the Georgia Tech family, having done her postdoc here at Georgia Tech as well. She's also been a distinguished Alexander von Humboldt postdoctoral fellow at the Fritz Haber Institute in Berlin. So she's got that international experience as well. So thank you so much for joining us today, and we look forward to hearing your perspectives right now.
Well, thank you very much for the invitation. I want to thank the organizers. I've had a really lovely experience the last 2 days. I enjoyed the poster session last night and getting a chance to go out to dinner with some of the students and hear about some of the things that have been going on. It's strange because I feel like I've spent half my academic life here at Georgia Tech because in addition to being a postdoc for a couple of years, I also was part of the Center for Chemical Evolution for like 8 years. So I was here all the time for a really long time. But I'm delighted to be able to talk to you this afternoon about what we've been doing at Kennesaw State since I joined the faculty back in 2011. And I'm hoping that I will tell you an engaging story because I know we're getting to the middle of the afternoon. Your lunch is like sitting a little heavier in your belly. And so, yeah, if I see anybody sleeping, I'm going to like walk right up to you. Okay, just be forewarned. Okay, so we are here. Sorry about that. In the astrobiology and origin of life community. And, you know, as part of this community, the overarching questions we are asking are, how did life arrive and could it exist elsewhere in the universe, right? These are the big picture questions. These are the questions that captivate the mind of my first year undergraduates, right? And get them to think seriously about doing research. But I'm going to be honest with you, I'm not going to answer those questions, right? We're going to pick that apart because we're all working on these two big questions, but we're taking some piece of that, right? And trying to understand that better. And so for a number of years, as a member of the Center for Chemical Evolution, we were really focused on trying to understand how proto-biopolymers evolved on the early Earth. And I was part of a team that was specifically looking at phosphorus. How did phosphorus become incorporated into our first biomolecules? So if we think about a biopolymer like DNA or RNA, our nucleic acids, right? Then the backbone is this ionized linker of phosphate. And if we think about things like our phospholipid bilayers, right, our cell membranes, we can think about everyone's favorite energy currency molecule, ATP, right? That P is for phosphate. So it's obviously really important in biological systems. And then more specifically, my group has been considering, okay, but how did you get it from rocks into life, okay? How do we actually think about phosphorus being released from minerals? So of the biogenic elements, the ones that are shown here, right, they all would have existed on the early Earth or even in astrochemical environments in fairly stable volatile phase species. So things like water vapor or methane gas or ammonia, right? But I have very selectively omitted my favorite one, phosphorus. And the thing is, there is a reactive form of phosphorus, phosphine, but it's so reactive. And when we think about the mechanisms by which you could make phosphine in some of these environments, it's hard to come up with a mechanism by which it would persist, right? How do you have enough of a concentration to build up for this to really be the source of phosphorus, especially on the early Earth, for example? And so that means that of these 6 biogenic elements, phosphorus is the one that really has to come from rocks. It doesn't really have another potential source. And so I'm not going to discuss all of this, but for a really long time, the Center for Chemical Evolution thought about different ways in which phosphorus could be coming out of minerals on the early Earth. And there's lots of great work that's been done. But today I'm going to talk instead about astrochemical environments. So places like the interstellar medium and circumstellar envelopes, and thinking about the phosphorus chemistry there. So if we think about phosphorus abundance in outer space, right? Phosphorus is actually a relatively low abundance material. It's something like the 17th most abundant element in the universe. And that makes it really particularly interesting for astrobiologists because it's so highly concentrated in life relative to its natural abundance in minerals. And we have some ideas about why its natural abundance in the universe is low, right? Astronomers believe that it's probably formed in massive stars. We don't have great nucleosynthesis models for it yet. They tend to underpredict a little bit. So this is still an open question, but we do know something about where it's observed in space. And if you look at the molecules that have been detected in the ISM, you notice that there's fairly few cases that actually contain phosphorus, right? So PN and PO are sort of the most abundant, and then CP, HCP, CCP, and phosphine is now considered a confirmed detection. There's also some tentative detections of NCCP. But really, the vast number of molecules that have been detected in the ISM are things that contain the other biogenic elements, right? And I will say this list is from 2018. Brett McGuire's paper is one of those papers that is being continuously updated, but he didn't have a table that fit conveniently on my slide that was more recent. So you get the 2018 version. And so one of the things that has been observed by astronomers is that there's really this situation of phosphorus species being depleted, especially in dense molecular clouds compared to diffuse molecular clouds. And that's created some questions, but really the hypothesis here is that solid grains in the dense molecular clouds are probably the primary location of phosphorus in those environments. And so astronomers have been trying to understand what those grains might be and how phosphorus is released from them. And so in the grand scheme of things, phosphorus volatile molecules haven't been detected for that long. So the first detections of PN and CP date back to the 1980s, like 1987, which is pretty late. And we're still at a place where like you can have a handle on all the times phosphorus molecules have ever been discovered, right? There are not that many papers for phosphorus molecule discoveries, and they're still being made, right? So earlier in so like a year ago, PO was, I think, first observed in the ISM. They didn't claim that exactly. They were like, it's the first time it's been observed in this direction, but I can't find another example. So I think they were like hedging a little just in case. And I love these spectra because, you know, I'm an experimental physical chemist. And when gas phase spectrometers get their rotational spectroscopy, it's like this delta function of a line. But I'm an experimental physical chemist who does chemistry on solid surfaces, and we have better resolution than this. So this is great. I'm like, oh, look. So these are just some ideas of some line spectra that have been observed. So the first detection, though, of phosphorus in a comet was actually not that long ago. And it was interesting because what they saw was atomic ionized phosphorus. And the question was, where did it come from, right? What's the parent species of this molecule that was detected in the mass spec of Rosina on the Rosetta mission? And I think Ravilla et al. Make a really great case for the fact that it's probably PO. And this is maybe a little surprising because PO is usually observed in lower abundances than PN in the ISM. And they hypothesized a mechanism for its formation. So they speculate that they think that grains containing phosphorus, which are found, you know, basically generate phosphine based on ALMA observations in outflow regions where there's a lot of shocks. So high electron sputtering or energetic electron sputtering. And they say, okay, we think that this phosphine is generated from the phosphorus-containing grains, that phosphine then undergoes photochemical reactions in the gas phase above the grains, and that photochemistry then produces PO, which then can react to make PN. So PO is probably a pretty important species in this cycle, but their argument is that it's actually the phosphine that's coming out of the phosphorus-containing grains. And so I'm going to take a little bit of an aside to point out some work that came out a few years ago from John Plain's group in Leeds, where he talks about the ablation of interplanetary dust particles in the atmosphere of Earth. So this is not the ISM. The conditions are obviously very different, but I think it's useful to take a look at this. So if you are in regions where you have ablation of meteoritic particles that contain phosphorus, so these are still small dust grains containing phosphorus, and you have the presence of some oxygen around, right? So in our atmosphere, we obviously have O2, we have water vapor, we have CO2, so there are lots of potential sources. But he's considered a pretty wide, or they've considered a pretty wide photochemical net or gas phase chemical network. And what's interesting is that they actually see two primary sinks, so phosphite and phosphate. And these sinks then go on to react with metal atoms in the gas phase. They modeled primarily iron, sodium, and magnesium because those are the most prevalent in our upper atmosphere. And what they see is a fairly large deposition of metal phosphites. We're going to come back to this. And so if they look at global averages, they say, well, we think maybe 10 to 11% of meteoritic smoke particles contain metal phosphites. And this might actually be a pretty important source of bioactive phosphorus that could be important not just here, but maybe elsewhere if we're thinking about other environments. Okay, so this is kind of an aside, but we are going to come back to it. The latest hypotheses about phosphorus in extraterrestrial spaces, so the ISM and circumstellar medium, comes from a paper by Bergner et al. So this is out of Karen Oberg's group. And they looked at PN and PO in a low mass star region, actually. And then they compared the distribution of these molecules to some other species. So in particular, they looked at how the PN and the PO related to SiO, which is a marker for silicate grains. And they make the argument that it doesn't seem to be cospatial with the SiO, and that it seems to be somehow constrained by the CCS. And they also looked at how the appearance of PN and PO relates to SO2 and methanol. And so the regions they're considering are areas where there isn't a lot of thermal processing, but rather there's more shocks. And what they see is that, or what the hypothesis they make is that the spatial regions where we see PN and PO don't align well with silicate grains, which means it's probably not sputtering of grains that are like silicates. They do seem cospatial with more volatile species, but since PO and PN aren't observed in regions where there's thermal processing, then we're probably looking for some kind of phosphorus-containing mineral that's less volatile than a silicate, but more volatile than a silicate, but less volatile than an ice. Okay, because if it was as volatile as methane or SO2, then we would also expect to see it in regions where there's thermal processing. And because it isn't cospatial with SiO and then it's probably not just trapped in rocks. And so this has really led to some questions about, okay, so what kind of material are we talking about? What are the phosphorus minerals that we need to be thinking about if we want to try to understand phosphorus cycles in extraterrestrial environments? So my research group is targeting these key questions, right? What are the phosphorus-bearing minerals that were important? We've looked in the past, primarily considering the early Earth, and now we're thinking more about extraterrestrial environments. What conditions do these minerals, or under what conditions do these minerals release their phosphorus? And what are the key phosphorus-bearing species that we should be looking for, right? Is it phosphine? Is it PO? What do we think we're going to get out of these systems? And we are doing lab-based astrochemistry to do this. So I'm going to talk mostly about two different classes of compounds, but we'll start. These are the three that we've looked at in my lab. So the first mineral is a meteoritic mineral called schreibersite. This is kind of an unusual species. It's an iron nickel phosphide. The phosphorus is actually in a slightly negative oxidation state, which presents some unusual chemistry opportunities in terms of oxidation chemistry. It is technically a semiconductor, but in many ways it has the characteristics of a metal alloy. So the band gap is so small that in effect it is actually conductive. It is magnetic, just like solid iron would be because of the high concentration of iron. It polishes up really shiny, so it's got luster. and a density that's very similar to iron. Another, like on the other extreme side, right, are phosphate minerals like hydroxyapatite, the things our bones are made of, also the predominant phosphorus species in the crust of the earth. Okay, so in this case, the phosphorus is in a +5 oxidation state, fully oxidized, and it's the most common and prevalent in biological systems. But in terms of trying to understand early Earth chemistry, it has very low solubility in water and very low reactivity for phosphorylation in water. So it is a material that is sort of the end state of phosphorus when we think about the life cycle. And then in the middle is this class of compounds called metal phosphites. They are potentially a really important intermediate species that hasn't been investigated very much. They are relatively soluble in water, actually. And the oxidation state being +3 means that they can undergo different kinds of, they can either be oxidized or reduced, right? They're sort of in the middle, which presents some unique opportunities in terms of the chemistry. They're also susceptible to acid-base chemistry. They're a weak acid. So there's a lot of interesting potential properties for these materials. And so my lab has become really interested in understanding these lately. Okay, so we're going to start by talking about schreibersite. This is the most common phosphorus-bearing mineral in meteorites, and the predominant composition is 2 irons, 1 nickel, and a phosphorus. But it can be any combination where you have 3 metal atoms per phosphorus atom. We can make it in the lab using iron and nickel phosphide powder, so you can't buy it commercially as a single crystal solid. That would be too easy. We have to make it. So we take a powder, we press it into a mold, we heat it for a while, we go through a whole series of polishing steps because we really need our surfaces to have a mirror finish. And I'll come back and talk about why in a little bit. And then we analyze it with SEM just to make sure the morphology is good. And we can do elemental analysis to see the distribution of the iron and the phosphorus and the nickel on the surface. We are primarily using a method called RARES, or sometimes it's called IRIS, but it's an infrared reflection technique. With the exception of my 2 students in the back, I'm guessing most of you don't know how it works, although there might be a few people. I won't go through all of it, but basically there are special selection rules for this method. And so the main takeaways here are that in order to see signal, you need the solid surface to be conductive so that you get the creation of an image dipole. This gives you a signal enhancement. We are only really able to see vibrational modes that have at least some component that is perpendicular to the plane of the surface. So if things align on the surface horizontally or the vibration is horizontal or parallel to the plane of the surface, we won't be able to detect them. And the signal intensity will scale with the angle of that vibrational motion. There's also a neat trick you can do. I won't talk about it very much today, but you can flip the polarization of the light. So it turns out that only the P polarized component of the light interacts with the solid surface. It undergoes about 170 degree, phase change. So, a 10-degree phase change for the P polarized component. So you still get constructive interference, but the S polarized component undergoes like 170-degree phase change. So it basically doesn't interact with the solid surface. But that presents an opportunity where you can flip the polarization of the light. And so you can use this RARES technique to actually look at liquid solid interfaces as well as gas solid interfaces. And we've done some work on hydroxyapatite thin films where we've done that technique. We also have to work in an ultra high vacuum chamber for some of these measurements, for the RARES in particular, unless we're doing the PM iris. And so I thought I would show off some renderings my student Tyler has done recently for his thesis. But we have, in addition to the infrared that goes through and reflects off of our sample, we also have an electron gun, so we can do electron irradiation. We have a small QMS, so we can do some mass spec measurements of our samples and look at volatiles coming off the surface. We don't have them on here, but we have, well, this is a Faraday cup, so we can measure our electron flux. We also have a helium UV source that we can put on and an ion source that we can put on. So we have different ways that we can irradiate our system. And then we have a cryo head that lets us cool down to at least 90 K as of today. It's fairly new to the system, so we're very excited. And that's even at pretty high pressure. In the end, this chamber will be down below 10 to the minus 9 torr, and the goal is to get down below at least 50 Kelvin so that we can really model some ultra cold systems. The second class of compounds that we want to look at, these metal phosphites, you also cannot buy commercially because that would be too easy. The synthesis is very straightforward. So you just react sodium hydroxide with phosphorus acid and you make sodium phosphite, and then you can react that with the metal chloride. And it works pretty well. You get these nice powders over here. There are a number of natural formation pathways. And so we think the relevance for this on the early Earth is pretty good. And in terms of astronomical environments or extraterrestrial environments, we are thinking about whether this might be something that's important. And so we'll talk about that in a minute. One thing I want to point out about the phosphite structure is that it contains a phosphorus hydrogen bond, and that turns out to be a really important way that we identify our metal phosphites. And I am part experimental physical chemist, part analytical chemist. So we just use whatever we have available to us. I'm not going to talk about all these methods, but in particular, the infrared and the NMR are important for analyzing our samples and being able to characterize them in the metal phosphite project. We do have a technique for looking at hydroxyapatite using PM-Iris, and that involves growing thin films of hydroxyapatite. Using electrochemical deposition. It works pretty well. There are some constraints. If you want to do infrared on a thin film of something that's not conductive, you need a conductive surface underneath, and the thickness of your film has to be less than the wavelength of your light. So we're growing films that are very thin, and that creates some unique challenges. But we have been able to do some in situ experiments looking at hydroxyapatite thin films reacting with low water activity solvents. I'm not going to talk about that much, but I have backup slides if you're really interested at the end. Okay, so the Center for Chemical Evolution spent a lot of time thinking about schreibersite as a potential reactive source on the early Earth for phosphorus. And one of the things that happened even before the center was to look at meteoritic samples of schreibersite and how they corrode in water. So these are two samples of this. Oops, I'm going the wrong way. I don't know if I can say this. Does anybody know how to pronounce this? Samcan palisite. This sample was showed in a paper in 2008. Here's a little bit of schreibersite, and the major things that are coming off are phosphite, which are these two peaks here, and phosphate, and a little bit of hypophosphate. And then very recently, Maheen Gull and Matt Pasek took some samples of this meteorite that they had shaved and stored for 8 years, and water and air, and they did PNMR on it again to see how it changed, which was really a cool experiment. And basically what they see, and is probably not that surprising, is that the phosphite oxidizes to make orthophosphate, and that you also get some dimerization to pyrophosphate, and you still have this persistent hypophosphate peak. So this is what happens when you put schreibersite in water. You get a bunch of phosphite. That's important. They also observed that schreibersite can be a starting reagent for creating organophosphates, which is really a central question if we're thinking about the formation of biomolecules from rocks. So you stick a chunk of meteorite in water with glycerol or some adenosine, and you just have to heat it a little bit. You don't have to go too hot, like 80 degrees Celsius is enough, and you'll get the formation of organophosphates. So they see glycerol 1-phosphate, and they actually made 3 different variations of adenosine monophosphate under these solutions. So this is pretty interesting chemistry for schreibersite. And so we decided that we would look at how small molecule ices interact with schreibersite to try to understand the phosphorus release. And so we deposited water and methanol and formic acid onto our schreibersite surfaces. And you can get an idea about our general signal to noise in each of these experiments from the black line. And then as you go down, this is increasing our amount of dosed small organic molecule onto the, or small molecule onto the surface. And if you look at these peaks, they are exactly what you would expect if you had a sheet of water or methanol or formic acid ice. So there are no features here that actually correlate to the Schreiber site surface interacting with these small molecules. Now, at the time, we were limited in temperature. And so these experiments are all pretty cold, 125, 120, 135 Kelvin. So it's perhaps not that surprising. We did see some evidence of oxidation. So the shifts of some of these peaks are what's been observed if you were depositing formic acid, for example, on an iron oxide surface. But there's really no features that indicate that the phosphorus is being activated under these conditions. It was kind of a disappointing result. But it was not a bad result because nobody had ever been able to do rares on anything but a metal before. And we did it on a metal phosphide. And it wasn't entirely clear that it was going to work based on the selection rules. We just knew that it had properties that were very similar to metal alloys. And so we had a proof of concept, at least, that the technique was functioning, but that our conditions were not good for releasing phosphorus, right? So at these temperatures in vacuum, you're not going to see anything, right? You have to have either a higher temperature or some other energy input to the system. And so my master's student at the time was like, I'm going to do this Hail Mary experiment. I'm just going to keep the sample at room temperature and dose it with a ton of water, right? The sticking coefficient is going to be low, but I'm just going to sit here for like an hour and a half and pour water on my surface and see what happens. And so the blue curve is the experiment at 130K, and the red curve was the experiment at 295K. And I will say the exposure of the water to the sample is at these elevated temperatures, but all the spectra have to be taken at 100 Kelvin to be able to have like a good background. And so when we did that, we saw this peak at 24, 23 wave numbers. And we were like, awesome, that's got to be something with phosphorus, right? We can't find anything else. It must be somehow related to phosphorus. We don't know exactly what it is, right? We sort of hypothesized, oh, it could be some kind of hydroxyl bound to a phosphorus on the surface. Maybe, I don't know. But we didn't really have any good way of identifying it. But we did have other experiments that we had done with hydrogen peroxide, which we had thought were totally dud experiments. We were like, man, nothing happened. But once we saw this peak at 24, 23, we went back and looked more closely at the peroxide experiments. And we were like, oh, it does look like maybe we had it with this strong oxidizer, even at low temperature. That's kind of interesting. And so for a long time, this just kind of was out there in the literature. And then last year, a group in Italy and Spain did some theoretical predictions on Schreiber site surfaces. And they analyzed it and looked at water on Schreiber site and said, oh, it's maybe some kind of proton transfer between the water ice above the Schreiber site surface. And I was like, okay, that's weird, but sure, you're doing a calculation. I'm not sure. And then we talked to them in September and they were like, no, that's totally wrong. Don't tell anybody that anymore. And we were like, okay, well, that makes me feel better. And they were like, no, we think it might actually be the pH stretch in phosphite. Now, their paper hasn't come out yet, so I can't show you anything, and I'm not going to tell you their names. But it is in the review process, right? So they actually think that's what's happening on the Schreiber site surface is that you're getting oxidation and you're making phosphite. You're making a thin layer of phosphite, and that's what we saw potentially in these experiments. So we are really interested in this, and we are actively pursuing some experiments now looking at Schreiber site. We're trying to get to colder temperatures and to be able to look at electron irradiation and UV light flux on these ices on Schreiber site to try and see if we can actually recreate this at low temperature, just with a different energy input. But in the meantime, we were in the CCE and they didn't really care about Schreiber site that much. So we were looking at other things that might be more feasible on the early Earth. And so we spent a lot of time, it turns out, looking at metal phosphites. And so we've spent some time synthesizing and then characterizing these metal phosphites. So from the perspective of for the infrared spectroscopy, you'll see that there are features corresponding to the bend in water and the stretch in water. And then this frequency at 2436 is the pH stretch in the phosphite. The amount of this OH stretching feature that you see over here really has to do with the number of waters of hydration on these metal phosphites because they're all hydrated to some extent. We have good correlation between infrared spectroscopy and Raman spectroscopy. And And then we use a lot of phosphorus NMR in our experiments because the coupling constant for the phosphorus hydrogen split when you look at the coupled spectra is actually very diagnostic for a metal phosphite. And the other thing that you should sort of keep in mind as you're looking at the data is that phosphorus NMR is very sensitive to pH. So the fact that these peaks don't line up perfectly has to do with how close the pHs are. The other thing that you'll notice is that all the iron phosphite experiments are done at pH 10, and that's because iron is magnetic and you got to precipitate the iron cations out of your solution or else you get nothing. You get a big blob of noise and nothing else. We've historically looked at pH 4 because that was a great pH when we were looking at phosphorylation of nucleosides, which was something that was very interesting in the CCE. So we have this kind of split pH data. We do a little X-ray diffraction in our lab. And so we have a pretty good agreement between the calcium and the magnesium phosphites and the standards, which is a good way to sort of confirm the numbers of waters of hydration. We've had difficulty finding standards for the iron phosphites. We do have a monochromator on our X-ray diffraction, so we can kind of address the iron, but anyway, it's been a little harder to pin that down with X-ray diffraction. One of the questions we had about these phosphites is how robust are they to oxidation? Because here's the thing, while there are several different ways that you can make metal phosphites in solution or on the early Earth that you can sort of think about it, right? Like if lightning strikes apatite, it will reduce it and give you phosphite. Now, how often does that happen? I don't know. You get some, but not tons and tons, right? But there's not a lot of evidence of phosphite in the geological record. And part of our argument is probably it doesn't persist, right? You can only see in the geological record what persists in the geological record. It doesn't mean it wasn't there on the early Earth. It just means we can't see it very well now. So we've been doing these thermogravimetric analysis measurements to try to understand how robust these phosphites are to oxidation. And we got this really perplexing result. So this TGA would make sense in air, but it looks exactly the same if you do it in argon and nitrogen. And there should not be any oxygen in our argon flow or our nitrogen flow. We've checked. We also did it at 2 other locations because we were like, maybe it's just our TGA. And it persists. And this is just a difference plot so that you can more easily see this big oxidation peak for the calcium phosphite. You can also see, when you look at these drops, it's not clear, but if you plot them as a difference plot, you can more easily see that there's different types of waters of hydration. They're not all bonding with the same strength within our metal phosphites. So we did a series of NMR experiments where we took samples, we heated them in a tube furnace to a certain temperature, and then cooled them back down and redissolved them so we could look at what was happening structurally to our samples. And what we observed was that by 300 degrees Celsius, you start to have oxidation of the phosphite to make phosphate. And that around 400 degrees, although it's hard to see in this plot, we had to go to more scans, you start to see oligomerization of the phosphites. And so this was kind of an interesting result for us. It's probably not unexpected, but what was unexpected is that the type of oligomers you make depends on the cation that's in the metal phosphite. So I'm only going to show you calcium for the sake of time because I am being mindful of the time. But we can actually see that we make, for example, some pyrophosphite and we make pyrophosphate, right? And there's a difference here. And in the case of iron, we actually see a really weird isohypophosphite, which is one of each, one phosphite and one phosphate. And so there's some question about how much oxidation you'll get, depending on whether you're looking at a calcium phosphite as your initial material, or if iron is there, because of course, iron is another thing that could be oxidized in place of the phosphorus. And so that seems to change the ratio. The other thing that was a little interesting is that in the infrared, we see differences in the spectra right at the point where the waters of hydration start to leave. So we identify this very clearly as a pH stretch. And then as we heat, we see that this pH stretch shifts. It blue shifts though, okay? So that would suggest that the strength of the pH bond is actually increasing, which was not really what we were expecting because we were thinking that we are seeing oligomerization. And so if the mass is increasing, right, that the pH stretch is associated with, then I would actually expect the shift for the pH bond to potentially redshift, right? Because mass is inversely proportional to the frequency, but it blue shifts. And it turns out that where it occurs is right where we start to lose our waters of hydration, which got us to thinking that maybe the issue is that initially somehow the waters of hydration are interacting with the pH bond, causing it to be redshifted. Now, here's why that doesn't make any sense. Because a phosphorus hydrogen bond is like one of the most nonpolar bonds you can have. So why does the water interact, right? This is not, this thing should not want a hydrogen bond, right? And so we don't have a good explanation. We would really like someone to do some modeling on this system and tell us what's going on, because it does look like somehow the water is influencing this pH stretch. And if we look in the PO region, which is way more complicated and difficult, so this is a mess of phosphorus oxygen bends and stretches, but we also see, you can kind of see there's a shoulder here at 1173, and you can also see here, as you start to heat, there's some shifting of the peaks in the blue. So we do think that there's an influence of water somehow interacting with our phosphites at higher temp, and as it leaves, right, the frequencies shift. We were able to confirm that the reason the TGA shows oxidation even in nitrogen and argon is because the thing that's doing the oxidizing is not O2, it's water. So what's happening is that the water, some of the water vapor from the waters of hydration is probably sticking around in the TGA, but also as you're heating, right, you're oligomerizing, you're releasing water, right? Because it's a condensation reaction. And so that seems to then be oxidizing the phosphite. And the way that we confirm this is that we pre-dried our sample. So we drove off all the waters of hydration, and then we did some isothermal experiments. And you can see there's a significant, right here, these were not pre-dried samples. And when we do the isotherms, we do see oxidation, but if we pre-dry it, it's pretty much a flat line. We also had done some high temperature isotherms, and they showed this really weird oscillatory behavior. And we started doing some research in the literature, and it looks like it might be based on particle size. So we tried sieving our samples, and you can see it does make a difference. So we think that basically the porosity of our sample is giving us some strange effects, even when we're holding our temperature constant. And so the thing is, it's very nice to have characterized these metal phosphites. We now have a better handle on them, and we're doing some more measurements to try to understand, if this could be the more volatile than silicate, but less volatile than ICE's material, right? That's on grains in astrochemical environments. But we're also interested in their reactivity in solution. And if they could potentially have been a reactive source of phosphorus on the early Earth. And so it's a two-step process if you want to start from a metal phosphite. You would first do phosphonylation, and then you need some way to oxidize the organophosphite into the organophosphate. And the advantage of doing phosphonylation is that phosphites are way more soluble than phosphates. And so you start with a much higher concentration of phosphorus in solution. And so potentially you get higher yields of the phosphonylated species. Now, the oxidation, we're primarily using Fenton's reaction. We've also explored a little bit of iron chloride and sodium sulfide with UV light as alternative oxidation pathways, and they haven't yielded the same results. But I will quickly show you that if we mix our samples with glycerol at 60 degrees Celsius and we dry them overnight, which is pretty much till they're dry, we can use very soluble phosphites like sodium phosphite or ammonium phosphite, and we see both the alpha and the beta glycerol phosphite. But even with calcium, which is way less soluble than the sodium and the ammonium phosphite, we still get phosphonylation. What's interesting is that the ammonium phosphite did seem to also to phosphite at multiple sites, to phosphonylate at multiple sites. And that was confirmed through carbon NMR, which I didn't bring, sorry, but I have it. If it's on my computer, if you need it. And these are just zoomed in. And then if we do Fenton chemistry, we can get an organophosphate. Now, we don't have yields yet, we're working on it. It turns out it is not as trivial as you might think to get a % yield if you're an experimental physical chemist who doesn't really do that much NMR. So this is ongoing work in the lab, but we do see the formation of phosphate, or sorry, yeah, the glycerol phosphate compared to a standard in our samples. Okay, so we have big plans, right? But I am at a university where research is done with mostly undergraduates and a master's student. And so, we move a little slower than maybe you do here at Georgia Tech. But where we are right now is actually a really great place because we have the methods to synthesize multiple different kinds of phosphorus-bearing minerals. We have a good experimental setup for being able to analyze the surface of materials like schreibersite. And we're really ready to dive in and do more reactivity studies. Obviously, we have some, but there's a host of experiments that we're looking forward to doing in the next couple of months. And in particular, we're curious about whether metal phosphites might be a key intermediate species that has kind of been neglected by the community and not really thought about too seriously. And we're working hard to recruit people to do calculations of some of these phosphorus-bearing mineral surfaces so we can better interpret the results we have. So I collaborate a lot. So Matt Pasek at USF has been a primary collaborator for like more than a decade. And then Tom Leeper is an NMR protein, NMR structural characterization guy, but he is also just like the NMR guy. So he has helped a lot with the experiments looking at the metal phosphites in solution. And we have a new collaboration with Donna Kassim, who is recently a research scientist at SWIRI, but she was my very first master's student. And so it's very exciting for me. She did all the schreibersite experiments, and now we're going to do more schreibersite. And so, yeah, I'm pretty stoked about that. So Tyler Davis, who's here, is my newer master's student. He did those beautiful UHV renderings, and he's been the one working hard on getting the UHV chamber. And then Thomas and Ellie are working on the metal phosphite project. Amelia is leading that metal phosphite project. And Gabby is working with Tyler on the schreibersite work. But I also want to acknowledge the fact that I have had a lot of students work on these projects over the years. So the people who are in bold and pink have been like the leaders of these different projects. But I think this is one of my biggest things is that I love the research that I do. I do think that we're providing and contributing to the community in terms of knowledge, but the biggest thing we're doing is training the next generation of astrobiologists and astrochemists. And that is something that I take a lot of pride in. And so I'm really thankful that you guys invited me to come and share this work with y'all. And then I will close just by saying I'm trying to recruit more. So we don't have a large astrobiology presence at Kennesaw State, although I will say I'm on the astrobiology listserv for Georgia Tech. And so you'll see my student, if you look and there's a name that's unfamiliar, it's probably one of my students. Whenever I have students reach out, I'm like, oh, you should go to this seminar. Here's the link because they can join the Zoom. So I really appreciate your community welcoming us and letting us kind of participate. And so I have this course. It's really focused on basically teaching undergrads P-Chem, but they don't know it. It's like hiding the vegetables in the marinara sauce, right? And so it's been really fun. We concentrate a lot on transferable skills in this class. So they do a lot of communication skills. Their final project is a poster. And I was so excited because the Adventure Twins was actually one of the posters in the spring. So they talked all about curiosity and perseverance. So they have to take a mission. They could pick whatever mission they want, and they have to relate the data that was collected in the mission to one of the fundamental physical chemistry concepts that's brought into the course. And so it's a good way to help them understand that what they're getting in Gen Chem is actually applicable, right? They have to kind of think about it. But okay, so thank you for listening, and I'm happy to take any questions.
Hi, thank you so much. This was a really fascinating talk. So something early on that really captivated my interest was you mentioned the different phosphorus-containing species that were detected in the coma of a comet. So I'm wondering about like the temperature and the time processes in there. Do you think it was more likely that it was the PO or the pH3 that was preserved for the billions of years in a comet? Or is that reactions that are happening now and it was stored in more like a grain up until a perihelion pass? Or what sort of processes do you think are happening elsewhere in the solar system right now?
Yeah, it's a great question. So the answer is, I don't know. And actually, it's an active debate. I think that Revilla et al. Did a really great job of showing that it's the parent molecule of that particular ionized phosphorus is probably not phosphine. So they did look at several different contenders, and they were able to pretty clearly, it's not definitive, but I would say they have very strong evidence for the fact that it came from PO. Now, the question is, was the PO trapped in the ice, or was that part of the sputtering process, right? Did it get formed as it was sputtering? And so that's actually what we're going to try. There are several groups that have looked at like phosphine water ice mixtures and phosphine organic water mixtures. But doing surface analysis off of these phosphorus-containing minerals is non-trivial. And I think we might be the only group that does it. So we're really excited to do it. But I don't think anybody knows what happens when you sputter schreibersite, right? And what happens if you sputter schreibersite with water or with hydrogen atoms, or, there's actually some modeling that looks at the reactivity of phosphorus with water versus hydroxide and the different chemical pathways and which of those are the most favorable. And at least computationally, it looks like the path with hydroxide is probably the most important, as opposed to with water, which is kind of a bummer because I don't know if we're going to see that in the lab, right? But yeah, I think it's still really an open question. And we're curious about, are you more likely to generate phosphine? And then is it really all about the gas phase chemistry? Or can you get PO off the surface? Because there's clearly a lot of oxidation of schreibersite. There's iron, right? So it oxidizes really fast if you have any water vapor around. And so, my hypothesis is that we'll see PO, but I don't know for sure.
Thanks so much. So I was curious about basically the survivability of these phosphines and these phosphates in solution. For example, you showed that there is some polymerization there, and you have like a nice triphosphate, right? And so then all you need is the adenosine, and you get your nice ATP molecule. But what is the likelihood of an organic reaction versus some sort of condensation reaction into apatite?
Yeah, so I think it's very unlikely that you would take a triphosphate and phosphorylate an organic with that, right? That's pretty much not going to happen. There are conditions. So if you have low water activity, right? So this is the work that like Bradley Burkar worked on, right? If you can get low enough water activity of the solvent, then you can get phosphorylation of the organic. But I actually think that it's easier to start from phosphite and phosphonylate and then oxidize, just because the phosphite is so much more soluble. And there are mechanisms in place by which you could be creating phosphite in pretty large concentrations, especially under the conditions of the early Earth. Like right before the Great Oxidation Event, you would have had a fair amount of iron 2s in the ocean. And there are mechanisms for producing phosphite under those conditions that could yield pretty large yields. So Matt Pasek, it's Barry Hershey, I think, is the first author, has a paper where they did modeling, and actually it was quite high concentrations of phosphite that were predicted to be potentially in the early Earth oceans.
Yeah. So is there a sink for the phosphite that is not organic phosphorylation?
Sure. I mean, it can oxidize to phosphate, right? That's probably its biggest sink.
Thanks.
Okay, that was a great talk.
Thanks.
And really interesting. And I actually have a bunch of questions, but I'll just ask one.
Okay.
So I guess maybe when you're talking about the dehydration of phosphite, when you dehydrate it, you're probably pulling waters off of the oxygens, and maybe even there has to be counterions, I suppose, there, right? And so everything is getting reorganized. So it seems like with all that happening, you should be able to create some scenario to give you the right chemical shift, right?
Right.
I mean,
I just don't
could
know what
invent
it
one,
is.
whether it's right, but yeah. So you could, a lot of things are happening besides the direct interactions with that hydrogen on the P.
Right. And I do think it's probably somehow has to do with, the other oxygens as opposed to the pH bond specifically. It's probably about water interacting with the other oxygens on the phosphite that is creating the shift in the frequency. We just don't have any good way of modeling that right now. I showed the calcium data in part because it only has 1 water of hydration too. So the magnesium phosphite does not show any oxidation. It has 8 waters of hydration. So it's kind of interesting. Yeah, the differences.
So Anton Petrov here, who I think you know, has done DFT calculations on phosphate and not phosphite, but phosphate, and he could probably help you
It's
with
good.
that.
I should reach out to him.
Yes, reach out to
Maybe
him.
I can convince him. He wants to spend his time on that.
Okay, any other questions? If not, we can say thank you again to Heather for that wonderful presentation.
I wanted to thank both of our speakers again. We wanted to present them with some Georgia Tech astrobiology swag. We've got our special mugs that go to people that have contributed to our community. So thank you, Heather. And thank you, Amy. Thank you so much. So in just a moment here, we're actually going to have the giving away of the astrobiology certificates with Dr. Glass. And we also wanted to point out that we have stickers and t-shirts for folks in the astrobiology community that you'll be able to grab in the back in a second as well. So let me get the slides up for you, Dr. Glass. Yes, thank you. Oh, thank you, Dr. Hernandez as well. I'm sorry. I got the email from Jen and I was. I think we only have one, so we'll have Christina representing for everybody.
I guess I should say. Okay, so we want to give a shout out to all of our amazing astrobiology graduate certificate recipients. We've now had 22 recipients in the last 3 years. So a round of applause for all of them. And okay, and these are our beautiful slides with our wonderful folks who have earned it. And for those of you that are graduate students at Georgia Tech now or thinking of becoming a student, feel free to look at our website, and it's good to look at the classes that these people took, because this is good to think about the classes you could take, and whether you've taken all these classes, you might already be eligible for the certificate. And you can just hop on our website and apply in the form and get it yourself. So yeah, do you want to go through so this is Michelle Babcock. Let's all clap for Michelle. She's there. They are online right now, Michelle. And this is Christina, who we have in real life. Christina, you want to hand her the certificate? Yay, round of applause. Go up there. You have to represent for everybody. Representing everybody. Yay. Yay. And oh yeah, there we go. Okay. Recreate. Excellent. And then our next recipient is Alec Domator, who I think is online right now, who's from Maryland. So congratulations, Alec. And Claire is on a cruise on the ocean right now. So congratulations, Claire. And she also helped organize. And she helped organize and is a fellow, yes. And last but not least, we have Sohaj Singh, who also might be online. So you're there. Congratulations, Sohaj. Okay, and these are all of our amazing students from through the years. They're all wonderful role models of our program, as are everyone in the room. And so feel free to talk to any of these folks if you're interested in doing the astrobiology certificate, or the two of us. So yeah, one more round of applause just for fun. Thanks, everybody. Thanks for a wonderful symposium.
Oh, and we do have in the works a minor in astrobiology for undergraduates. And so please spread the word that is coming soon. Yes. But thank you so much again, everybody. Yeah.
Yeah. All right. Thanks, everybody. We'll hand it back to the organizers. And let's have a round of applause for our organizer.
Thank you both. And then this is just the one last plug also for the Georgia Tech Astrobiology Fellowship that will be due in April. We'd love to see the next round of fellows coming in. So with that, thank you so much for your attendance today. It is wonderful to see that the Georgia Tech Astrobiology community is thriving and that everybody is so interdisciplinary in this university, and we're getting to collaborate with peers in the South. And we just had incredible representation online through interest from the NASA Astrobiology newsletter, which recruited some folks online as well. So thank you all for being here today. Make sure to grab your t-shirts and stickers to represent, and we look forward to staying in communication with all of you that love space as much as we do. Thanks.